All right, so now we're going to go over the main class of reactions that you can do with aldehydes and ketones. So keep in mind that when you have the carbonyl functionality here, that the carbon of the function of the carbonyl group is electrophilic, and the oxygen of the carbonyl is nucleophilic. And the reason this carbon is electrophilic and this oxygen is nucleophilic is there's both the resonance and the inductive effect. So from a resonance standpoint, the oxygen, I can push a pair of electrons onto the oxygen to make O minus, C plus. These are the formal, so clearly nucleophilic, clearly electrophilic. Also from an electronegativity standpoint, this oxygen is pulling electrons toward it, making this partially negative, partially positive. So all that's to say is that when you have a carbonyl, the main reaction that you can do with carbonyls and aldehydes and ketones in particular, the main reaction you can do with aldehydes and ketones is something that we call a nucleophilic addition reaction. This is where some nucleophile attacks and adds to the electrophilic carbon here to make a new molecule. So you're taking two things, making one thing. Notice that the carbonyl is planar here, sp2 hybridized. When you do the nucleophilic addition reaction, you're making a new sp3 tetrahedral center there. Okay. Now, when you think about aldehydes and ketones, you might think that maybe they have the same reactivity, and you'd be wrong. Aldehydes are generally more reactive toward nucleophiles than ketones. Now, this isn't a hard and fast rule. You can make ketones more nucleophilic than aldehydes by adding other electron withdrawing groups nearby to the ketone. But in general, if you're comparing similarly structured aldehydes and ketones, the aldehyde will be more reactive. And there are two reasons why you can think of aldehydes as being more reactive. One is that there's less steric hindrance around the aldehyde. So in ketones, you have two alkyl groups, and in the aldehyde, you only have the one alkyl group. So the hydrogen, not as big as the alkyl group, so the less sterically hindered carbon right here is this one in the aldehyde, making it easier to be attacked by a nucleophile. The other reason that aldehydes are thought to be considered to be more reactive than ketones is because the aldehyde has fewer electron donating groups in terms of alkyl groups. You can think of alkyl groups as electron donating. They kind of stabilize, they're kind of pushing their electrons this way and making this positive charge here less positive. So in the aldehyde, you only have one alkyl group pushing and stabilizing this positive charge. Here, you have two alkyl groups pushing and stabilizing this positive charge here, making this carbon less electrophilic because it's less electropositive. So aldehydes are more reactive than ketones. Now, when you do these nucleophilic addition reactions, these reactions occur under one of two conditions. We call them either acidic conditions or basic conditions. So let's go over what it means to add a reaction under basic conditions. An example of doing a nucleophilic addition under basic conditions is the Grignard reagent. So remember, when you see the Grignard reagent, you recognize this as the Grignard reagent. So really what you want to be thinking of this is as the carb anion. And because this is negatively charged, we think of this as being basic. So when we say basic conditions, this is really also referring to negatively charged reagents. Okay, so basically, in this case, under these basic conditions, your nucleophile will be negatively charged, and this means you're generally adding strong nucleophiles to aldehydes and ketones, things like hydride or the Grignard reagents. The general mechanism for this addition under basic conditions is shown here. So again, what happens here is you have the ketone of the aldehyde. This carbon's electrophilic. So there's a nucleophilic attack of the strong nucleophile onto the electrophilic carbon. That makes the alkoxide, and this is where the reaction kind of stops here. So if you go back to this previous slide, notice that there's two steps. There's the nucleophilic addition here of the strong nucleophile, followed by a proton transfer. So the nucleophile adds to make the alkoxide. Then there's a proton transfer from water. So the O minus attacks water to make the alcohol with a new nucleophile added to it. So when we're thinking about basic conditions, we're thinking about strong nucleophiles that are negatively charged. If we think about acidic conditions, then what we're really thinking about is we don't have strong nucleophiles. Usually we're thinking about weaker nucleophiles. And because they're weaker nucleophiles, we need to beef up the electrophilicity of the carbonyl carbon. In order to do that, we generally will have some protic, something that's protic in there. HX, sulfuric acid, HCl, tostic acid, paratoluene sulfonic acid, something acidic in there. And then the moment you put that acidic thing in there, whatever that H plus is, the moment you put H plus into it, those are acidic conditions. And the first step of almost every reaction under acidic conditions, so when we say acidic conditions, right, the tip-off that you're in acidic conditions is some form of H plus. This H plus, again, could be in the form of HX, it could be in the form of sulfuric acid, it could be in the form of HCl, it could be in the form of tostic acid, it could be in the form of paratoluene sulfonic acid, it could just be in the form of H plus that we write, or it could even just be H3O plus, okay? So any of those things, when you see when you see any of those things over the arrow, you're under acidic conditions. And when you're in acidic conditions, the first step is always a proton transfer. And so here, the most basic thing on this molecule is the nucleophilic oxygen. So the oxygen attacks the proton, becomes an oxonium. Remember, this doesn't make the oxygen more electronegative, or sorry, it doesn't make the oxygen more electrophilic. It actually makes the oxygen more electronegative, which makes this carbon more electrophilic. At this point, whatever the nucleophile is, which is usually a weak nucleophile, that can attack that carbon to end up giving you the final alcohol product. And again, the reason why you need this protonation to happen is because in general, the nucleophiles that are adding under these acidic conditions aren't nucleophilic enough to react with this carbon here. But the moment I make the oxonium, remember, that makes this oxygen more electronegative. So there's this other resonance structure here that becomes really important. And you notice in this resonance structure, the formal positive charge is gone from the oxygen. It's on the carbon, which makes that a very important resonance contributor to this intermediate here. So when you have these weak nucleophiles attack the protonated carbonyl, you end up with this equilibrium between the starting materials and the product. And really what you want to do is, in order to understand where this equilibrium lies, is you want to look at the nucleophile that's adding and think about the nucleophile, the thing that you added, its ability to function as a leaving group. So what that means is if I take this aldehyde, if I take an aldehyde or ketone here, I react it with HCl, what's going to happen here in this case is my carbonyl is going to protonate here, kicking this out to be Cl minus. I'm going to make my oxonium here, right? And then Cl minus is going to come in and attack that positively charged intermediate to make this molecule here. Now, the chloride is acting as a nucleophile here, but the chlorine can also act as a leaving group. And we know chlorine's a really good leaving group. So in this case, because the chlorine's a really good leaving group, the equilibrium for this reaction is going to lie very much this way. So if I add HCl to this, I'm not going to make a lot of this. Most of my molecules will still be on this side of the arrow. Now what we're going to do in this chapter is we're basically just going to start covering different nucleophiles that we can start adding to aldehydes and ketones. Oxygen, sulfur, nitrogen, hydride, and carbon. So oxygen, sulfur, nitrogen, hydrogen, carbon. We're just going to kind of go over those different types of nucleophiles that we can start adding to aldehydes and ketones and doing nucleophilic addition reactions. All right, thanks for listening. Let me know if you have any questions, and thanks.